talk about the integral, so I'm going to just write the definition and meaning of the integral from the single variable. So here we have integral of a single variable function, single variable function, and this is defined to be the limit. Is it I? Yes. The index was I from 1 to n of xi. Let me write it this way. So just instead of using xi, it's a plus I b minus a over n, b minus a over n. So this whole expression is about n. We take the limit. If it exists, we say it's the integral. Or also, I warned you that this is not actually the most rigorous definition, because I'm kind of assuming that this function f is integral already. So if it's integral, then no matter what you take in this value of function, you always have a limit. It's the same limit here. But anyway, if you want to compute the simplest way, then this is one way you can get. And this is the same as the area under the graph on the interval AB. So now let's look at the double integral. So we have a rectangular domain, and you have a two-variable function. And this is both one expression indicating a value, and this is given by limit of double sum I from 1 to n, j from 1 to n. And here you want to plug in I b minus a here for x coordinate, and for the y coordinate you have j b minus c over n, and we have b minus a and b minus c n, right? And we say a function, two-variable function, is integrable if this limit exists. And okay, and then this is the meaning of this is the volume under the graph of this two-variable function on this rectangular domain. So from here, it gets interesting. So what we have, when we have a domain D, which is not a rectangular domain, but still lies inside a big rectangular domain, you can still take the integral over that domain of a function defined over that domain, and this is defined to be the integral of rectangular domain of function f times psi. So here psi is a multiple. So let me just write multiple symbol times psi dx dy, okay, where psi is 1 or 0 if xy lies in D, otherwise 0 here. So you can find the integral on any shape of domain, okay? Not just the rectangular, it can be anything, as long as it is contained in a rectangular region. So let me go a little bit further. So here we have cube. So here A, B, C, D, E, F. So what do you think this integral defines? So if you have three-variable function and you want to define whatever this is in a similar way to this, we did this here. So we use the limit n goes to infinity of 3 sum, so I from 1 to n, j from 1 to n, k from 1 to n. So we're going to subdivide the cube into n squared subcubes, and we're going to plug in numbers for x, y, z. A plus I d minus a over n, c plus j d minus c over n, and e plus k, f minus e over n, and then b minus a and d minus c and f minus e n. Okay. So if this limit exists, we say we call this value to be denoted as this. So there's a name. The first one is called the definite integral. The second is called double integral, and the third is also called double integral, and the last one is called the triple integral. The double, triple just means the dimension of the domain. So what is this? So the meaning of the integral, the single integral and double integral is clear. So this is volume under the graph over the rectangular domain, and this is the volume under the graph over this region D. And what would be the meaning of this triple integral? So we have area, volume, and what's next? So area is the size of two-dimensional region, volume is the size of three-dimensional region, and the next one is size of four-dimensional region. So what do you mean by size of four-dimensional region? Well, we call it volume. We can imagine what that is because we're not living in fourth dimension, but there is fourth dimension in mathematical settings, and there is a volume, the concept of volume. Just as we have a concept of volume of cube, there is a cube in fourth dimension. So if you watched the video, the movie, Iron Man or Avengers, you can remember that there's a tesseract. The tesseract is four-dimensional cube. And there is a volume that you can just multiply all the sizes of dimensions of the tesseract to get the volume of that four-dimensional cube. And in the same way we define the volume of two or three-dimensional region, you can define the volume of four-dimensional region. Well, but that doesn't really get to our sense. So you can kind of give a different meaning to the triple integral. So what happens is, let's say we have a three-dimensional cube here. So it's A, B, C, D, E, F here. And at each point, let's say this is X, Y, Z, is F, X, Y, Z. Let's suppose that this represents the density, the point density of this thing, whatever, metal or liquid, whatever. Let's say the densities differ by points. Then this triple integral of A, B, up to E, F of this function, X, Y, Z, is the mass of this thing. It makes sense. Why? Because look at the definition here. We have the volume. We have a volume of a small cube. Volume of sub-cube. Right? And what is this? So this is the value which can be density. Right? So basically we are adding density times the volume, which is the mass of small cube, which subdivides the entire cube. So when you add all the small masses, you get the entire mass. Of course, this is an approximation when you just simply add them. So when you take the limit, you get the accurate mass. So this is one way you can give a meaning to the triple integral. And you can go forever, actually. You can have multiple integral. You can have fourth integral and fifth integral. Just increase the number of variables, you can get the integration on any dimensional region. Okay? And let's say we have a volume, three-dimensional volume called V, and how we define the triple integral over V. Suppose that we have a function defined over V. So I can pick a point inside of V and find a value of function there. How do we get the triple integral? So the same way we did for this case. We put this V into a big box which contains entirely the V, and then we define it to be the integral on the big box f times psi dx dy dz. Okay? So I forgot to mention dx dy dz here. So what is psi here? So psi is a function of 0 and 1. It's 1 when the xyz lies inside of the region V, 0 otherwise. Okay. See. Any questions?
Can you move it to here because I can see it? Thank you.
Any questions?
No, I can see second.
Okay. You cannot see that. Okay.
I think it's better, yeah. Thank you.
Let's see. I'm gonna. Oh, okay. So we need to mention about the Fubini theorem. So okay. So here is the Fubini. Okay. This marker here. Fubini theorem. So if fx and fy are continuous functions, then the following follows. So suppose that we have, well, just before I mention what the is, just write the equation. So the double integration, the double integration over d of this function is given by this iterated integral, where d, so where what is g1, g2? They are the function that defines our domain d. So d is the collection of all points where x lies in between a and b, and according to what your x is, your y is in between these. I think you can. Can you see this? No, I don't think you can see this. Let me. Okay, so that's the simple Fubini theorem, and you can actually, so you have to be careful about this order, right? So we have dy first and dx. So I emphasize that this right-hand side is not double integral; it's an iterated integral. So we are taking an integration from the inside to outside, as if each integral is an integration of single variable function. So for example, if I take the integration of inside here, I take x as if it's a constant. Just consider this fxy is a function of y, and then just take the integration. And then what you get after taking integration inside is you get a formula of x. So then you take the integration in terms of x to get the value. So you can do the similar thing with the opposite, changing your x and y. So for example, your double integration can be written as the following. If your d is in the opposite direction, so we have y is from c to d, and x is from h1y to h2y. So for each y, you have a bound of your x from h1 to h2, based on your shape of your d. Then this can be computed by h1x, h2x, fxy, dx, dy. So that's Fubini theorem. So let's look at some example. I think it's important to see the example here. The easy one here is the following. So let's see, we have a double integral from 0 to pi and minus pi over 2 to pi over 2. And our function is -1 minus cosine x, sine x, sine y, dx, dy. Let's do this one. So there are two ways you can compute this. You can either just follow the definition. Okay, so what is the definition here? So you can take the limit and the double sum here, and take the limit by taking approximate value, by letting n to be quite large. Or you can use the Fubini theorem. So let's use the Fubini theorem first. So we have D to be the rectangular region. So you have to first find out what the G, or you have to first choose which one you're going to use. So let's say I'm going to use this equation. Then you have to find what G1 and G2 must be. So D here is a collection of points where x is changing from 0 to pi. Then y is changing. It doesn't matter actually what x is, because always y changes from minus pi to pi over 2 to pi over 2. So it's pi over 2 to pi over 2. So So this is going to be g1x, which is a constant function, and this is g2x. Okay? And the integration becomes first x and then y here. So our function is minus cosine x sine y, and this is about integration of y and then x. Okay? And then let's do the iterated integral. For the first one, now consider x to be constant, so just 1 minus some constant times sine y. So this becomes 0 pi y minus cosine x, which is constant, and integration of sine y, which is minus cosine, so it's plus cosine y. And then that's antiderivative. I plug in pi over 2 minus pi over 2. So what is it? Cosine pi over 2 is 0, right? Minus pi over 2 is also 0, right? So we get 0 in this part, and for the y part we have pi, right? So 0 pi dx. I'll throw out dx here. Okay? So now we luckily don't get any x here, so it's just pi squared. Okay? So let's do a little bit complicated one. So this one is simple because the domain is rectangular. But what if we have non-rectangular domain? So let's see. Here, let me draw the picture first.
Can I ask?
Yes.
Why first we have dx dy and then we have dy dx?
Why did I use the dy dx here?
And at the top.
At the top?
example, it's
Oh,
dx
this is
dy.
double integral symbol. So this is just one symbol here.
Okay.
So, well, you can use dy dx, but it really doesn't matter because this is the whole expression of what this means. And this is a different notation. This is an iterated integral. So it's kind of missing this big bracket. So it gives this dx, the dy dx order gives you the order of taking multiplication and integration here.
But we can solve it by dx. Even if we solve by dx dy, it will have the same values, but we need to change the order of.
Yeah. So if you want to change dx dy, then you have to change the limits here. So here, let's see. Let me write here. The d is yeah. Let me draw a picture first, and then show you how to look at it. D is here. So here we have 1, and here 1. So d is upper triangular of this square. So how do you write d in the expression something similar to in the Frobenius theorem? So you want to go for here and here. I mean, either works. So let's go for here. So in this case, if I want to express the d, then it says that I first take the range of x, which is 0 to 1, because that's the entire range of x in the coordinate of d. And for each x, I need to go for the limit of the lowest point and highest point, the minimum and maximum of y. So the minimum bit, the maximum is always constant to 1. So when x is chosen between 0 and 1, y, the value of the y coordinate is always less than 1, that's the maximum. The minimum depends on x, right? So this line is y equals to x, so y is always bigger than x, right? So if you express your domain for d, then you can use the Frobenius theorem, the first equation there. Suppose that I want to find the double integration of function 1 minus x squared over that domain. Let's see, times y here, and dx dy. This dx dy is just one thing here. How do I get it? So again, you can use the definition or use the Frobenius theorem. Let's use the Frobenius theorem in this case. So if I go for this, then this is equals to 0, 1, x1 of 1 minus x squared y dy dx, right? Y first, because I move my y based on my choice of x, and then you integrate x next, right? Well, let's try this. How do you get this? So first of all, you can think of this as square part times square y. So you consider x to be constant, so this whole thing is just one constant, so it comes out as a constant, 1 minus x squared. And then you take the integration of square root of y, right? Since x is always positive, it's okay to put x here, so it's 3 over, so 2 over y 2 third 3 2 of x1, right? And dx. So what is it? So 0 1 square root 1 minus x squared, and what? Plug in 1 here, you get 2 over 3 minus 2 over 3 x 2 3 here, and dx. So now you have a long expression, but it's about x, and this is just a single variable function integration. You can get it. Let's see. Yeah, so let's try to do this. It's complicated, but it's doable. So first of all, what is it? So I'm going to split this out into two parts. 2 over 3, 0 1, 1 minus x squared dx, and then minus 2 over 3, 0 1, and x 3 over 2, 1 minus x squared dx. So how do you take the integration for this part? So we talked about this last time about substitution using cosine and sine. So I'm going to substitute x to be cosine t here. So it's 2 over 3. And x is changing from 0 to 1. So we need to change x t to be, I can use sine instead of cosine. I think it's more easier. So t must be changing from 0 to pi over 2 to change x from 0 to 1. So it's 0 to pi over 2. And then the 1 minus sine square is cosine square, and square root is cosine t, and dt is another cosine t, right? So that's the first part. And how about second? So I'm going to do the same. So here we have, let's see. Why wait, so, root here. Oh, there's a typo in the book, there's some mistake. Let's see. Sine. Okay, so how do you solve this? Let's think about this a bit here. Let's see. Substitution. I think it's a bit complicated to solve this. It's not simple, right? So, well, let's say. I'm not saying that. It doesn't exist. Just saying that it's harder to find the antiderivative of this function and then just use the fundamental theorem of calculus. So let's suppose that we can get it by just, and also we know that this is integrable, this function is integrable because it's continuous. So let's suppose that we just found this value, the definite integral, by using the definition here. So what is the definition? So it's 0 to 1, so we get I over 1 as an x. So we get 3 over 2 times square root of minus I over n squared times 1 over n. So when you take the limit by taking approximation with large n, then we get some value, so we can get it. So here, it's simple, right? And you can even see that this is pi over 4, which is the quarter of this area of the circle. Anyway, so that's doable. So all I want to say is just you can do it by using the Robinet theorem. And let's try opposite way. So let's say, what if I don't use this way of expression? Instead of doing x first, let's say I do y first. So y is from also 0 to 1. And what is the min and max of x for each y? So x is always from 0. The maximum is y. So x can be from 0 to y. Right? So in that case, I can write the same double integration in the opposite order. So y first, 0 to 1, and x is from 0 to y. So, but the same integrand, 1 minus x squared y, so dx, dy, right? So you choose which one is easier. So in this case, what you have to do is first take the integration in terms of x. So basically the y is constant, so y square root of y comes out, and you have to take the integration squared dx dy. Well, I think you can do it I think you can do it here, because you can take the same integration by substitution here to get somehow some value in terms of arc sine or whatever. But I think it's getting harder the next point, because you have a square root of y times something in complicated formula of y. So, well, let me finish it, right, doing this. So here, what is it? When I take a substitution x to sine t, then it's integration 0 to sine inverse y of cosine square t dt, right? dy. So let's see, let me write it down here. So this becomes 0, 1 square root of y, and 2, 1 plus cosine 2t, 0 sine inverse y dy. So therefore this becomes 0, 1 square root of y, 1 over sine inverse y plus cosine 2 times sine inverse y, right, dy. Okay, well, complicated, but this is a nice function. It's just that you don't know what the antiderivative is. You can compute the value of function easily by using the Python or computation or calculator. So you can find the value by using the definition of the definite integral, taking the limit. So you can find it. So when I teach this kind of concept, definite integral, I try to emphasize that even though you don't know the antiderivative, you should be able to find value by going back to the definition, right? So you don't always go for the exact value, because after all, what you want is the number, evaluation of the number that represented by the decimals. So let me, so in the book, I think there's a type of big calculation mistake. So I'm going to go for another example. So let's see. Okay, so here's one better one. Another example. I don't have a working thing here. It's not working. This works. Okay, this one, let's see, our domain looks like the graph under the area under the graph of y equals to x squared from 0 to 1. So this is my d. So I can write d to be x is from 0 to 1 and y is from 0 to x squared. Okay? So when you read the definition here, you have to go for your x, because x is now doesn't depend on any other variable. So you can choose freely between 0 and 1. Once you choose that, it defines the bounds of the other variable, y. So I want to find the definite integral over d, or double integral over d, of cosine square dx dy. Sorry, q. So how do we do that? So again, there's two ways, using definition by limit or Fubini theorem. So let's go for Fubini theorem. So since we already mentioned d to be this way, so the Fubini theorem says that first x is from 0 to 1, and next y is 0 to x squared, and cosine x cubed, and go for dy and dx. So I need to integrate over dy first. X is a constant, so you can just take cosine x cubed outside. And inside, it's just the integration of 1, right? So it's just y, and from x squared 0, and dx. And this becomes 0, 1, x squared cosine x cubed dx. So now it's just integration by parts, or integration by substitution. So this is, I can do it without using the integration by substitution. Because I know that if you take the derivative of this function, then you get the integrand here, right? Just using eyeballing here. We have x from 0 to 1. So what is it? The 1 over 3 sine 1. Okay, again, it's what is x sine 1? We don't know, we have to compute. So I'm saying this is not the only way that the answer. So let's use the other way. So how about we use the second equation of Fubini's theorem was right here. And instead of using the expression of d like this, let's change the expression. So I want to set the y to be the free variable. Y is changing from 0 to 1 because that's the maximum y among all the points in D. And where is the minimum and maximum of x for each y? What is the minimum? Well, 1 is maximum actually. Yeah, 1 is maximum. What is minimum?
X, y squared.
Yes, square root of y, right? Because we want to follow the same curve. This points on this curve follows this equation. So when x is given, y is x squared. So when y is given, x is square root of y. So this is my expression of d. So then this can be written as, if I use this expression, then y first, 0, 1, and x next, square root of y, 1, and then cosine x cubed, in this case, dx and dy, right? So now the question is, how do I take this? Cosine x cubed. Of course, I can take it. I can give a definition of this definite integral by definition using the limits and so on. But the question is, my lower limit is not given as some number. It's a variable, right? So it's hard to find a formula in terms of y. I can go for the definition, but the limit will contain y, so it's going to be really complicated. So, so in this case, it's rather just stop here and then look for other ways of using Fubini's theorem, because it's really hard to get the formula here. So Fubini's theorem is giving you just a trick, kind of a trick that gives easier ways to find the exact answer. So I'll give you another trick. I'll give you another type of Fubini's theorem and then give you a lot more other tricks. So suppose that you may ask me this question before I give you another trick. So suppose that you have two different expressions and you have a two different way of applying the Fubini's theorem. What if both way doesn't work? Well, just then don't use Fubini's theorem. Just go for the definition of original double integral. Or what is it? So first of all, b cosine x cubed dx dy is defined to be the limit of double sum from I1 to n, j1 to n, and you plug in the values. Here x is I over n, right? And then there's no y, and dx dy is 1 over n, 1 over n. So basically I'm using the definition of the double integral over this rectangular domain, cosine x cubed times the psi dx dy. So I have a cosine cubed only when we have this psi value is 1, right? So how do you define psi here? So psi xy is either 1 or 0. So we want to be 1 whenever we have xy lies inside of this domain D, region D. So that's only when you have y less than x squared, right? So y is less than or equal to x squared. You can throw in equal sign here or not. You don't depend on your choice because the boundary really doesn't matter to the area. So anyway, that's your psi, and if you just plug the situation is that we don't plug in any real number xy in our formula. We only need to apply j here, I over n and j over n as x and y. So in that case, let's see what happens. So this is 1 or 0 if j over n is less than I over n squared, right? So it's the same as n times j less than I squared. Right? If your I and j satisfies this inequality, then this is 1. So otherwise, it's 0. So you make a loop in your so you don't want to compute by hands. You want to use the Python code or a computer program to compute this big sum by taking n to be quite a large number. And whenever you take a loop, you take a double loop here for I and j, and then you set a condition that when I and j satisfies this inequality, you want to add these values. Otherwise, you don't add it to your sum. And whatever the total sum is your double integration here. So you just go for the definition this way. If the Fubini theorem doesn't work in both ways. Okay, so we talked about the meaning of the idea inside of the Fubini theorem. So I'm going to give you another type of Fubini theorem, or triple integral. Okay. Let's say we have v to be given as the following. So we have x is from a to b, y is from g1x to g2y, g2x, and z is from h1xy to h2xy. Let's say this is our definition of volume v. Okay. What does that mean? So it's inside of three-dimensional space, and let's suppose that it looks like this. This is your v. And let's say it's kind of oval shape. Okay, there's no going, it's not a torus thing, it's just oval. So if I take onto a map, if I take a projection onto xy plane, I get a shade. And for each point inside of the shade, if I go up, then I take at most 2 points. I intersect at most 2 points in the volume of the surface of the volume. So here is the minimum, here is the maximum. And in between this minimum and maximum points, the entire line segment lies inside of the volume V. So what I'm doing here is, so these, so it is also, suppose that this is oval again. This is kind of oval here. So x, the value of x of points inside of my projection range from A to B. And whenever I fix x, my shade has a section whose y-coordinate follows the minimum and maximum here. The minimum curve and maximum curve follows the graph of function y goes to g1x and y goes to g2x. Okay? So it's kind of a same way of describing the two-dimensional region D. And whenever I fix x and y, let's say I fix x and y here, then I have a minimum and maximum value of z coordinate inside of this region V. So somehow there is a boundary that splits our volume. And the lower part, the minimum value consists of some surface, and this surface is a graph of h1, and the maximum is the graph of h2 here. So this is my setting. So I have a volume. All I want is the boundary of the volume that defines the shape of the volume, and I can split the total boundary into two parts, which gives the maximum and minimum, and both have the same shade when I project it onto xy plane, and this shade is also bounded by two curves which are the graphs of g1 and g2 function. You can see here the equation is given here. So now, if I want the triple integral of the three-variable function f dx dy dz, then Fubini theorem says, there is also a condition that this integrand is continuous whenever, even if you take the partial derivatives. So fx, fy, fz are all continuous function. But let's skip that because it's always the case in our example. So x first, and y and z. h1 is y, h2 is y, f, x, y, z, dz, dy, dx. Okay, so this is the Fubini theorem. These two are the same thing. I'm not saying that they are conceptually the same. They are two different things. One is the triple integral defined by the limit of the triple sum. And the second here is defined as the iterated integral. So you're taking an integration of the integrand in terms of z as if x and y are constant. So you get something in terms of x, y after you take the integration. And then you take the next integration in terms of y as if x is constant. So after taking twice of this integration, you get a formula of x. Then you take the final integration in terms of x to get a number. And this number, the Fubini theorem says that this number is same as the triple integral. So what does this mean? What does this, why is these two things are the same thing? So go back to the meaning of triple integral. What was the physical meaning that we gave from the beginning? This volume, integration of triple integral over the volume, is the mass of this volume if the integrand f is the density, point density, right? So in some sense, this second equation gives you the volume, the mass of the volume. So look at the first integral, the innermost integration here. So what you're doing here, you fix xy, and you're moving your z coordinate within your volume with a small line segment inside the volume here, right above this point, and you integrate your point density over this line. If you integrate density over line, what do you get? You get the mass of a line segment. So think about actually you having a thin wire standing above this shade here, shaded region here. So you get a thin wire, and each point in the wire you have a different density. You get the integration over this wire gives you the entire mass of the wire. So here there's no physical thickness, so we just consider this is the mass of a line. So you get the mass of a line, and then you take the second integration over y. What do you get? So you're changing your y from this over this line segment. So after at every each point y, you get the line segment lying above this point, which is covering entire section of your volume over this line. You kind of get an area, right? And you're not integrating the length of a line, you're integrating the mass of a line segment. If you're adding all the masses of the line segment inside your section area, then you get the mass of an area, right? So after taking this two integration, you get the area of a section, mass of a section. Section cut at x. And then you take the integration over x. So you get the mass of sections at every point. You integrate over x, you get the mass of entire three-dimensional region. So that's the same meaning as original triple integral. Okay? All right, so let me give an example. So here it gets interesting for me at least. When you have a Fubini theorem of this triple integration, if this thing h or g is given, it's easy to write down the formula, but sometimes the volume is not given as this form. So you have to find your g1, g2, h or h2. So let me give a quick quiz about this. So suppose that we have this kind of figure that you have b equals to x from 0 to 2, y from 0 to z, x, and z from 0 to y. Okay, so we have this definition. I want to change the order of x and y and z. So what I need is I want to see the figure of this domain, let's call it V here. Let's call it V. And I want to draw the figure of this domain V in 3-dimensional. What does it look like? So look carefully about the formula again. So when I write this way, then you have to go from left to right. So x is now freely changing from 0 to 2. Once x is fixed, y is now only changing from 0 to x. And when x and y are both fixed, z is changing from 0 to y. So z is not dependent on x, so you can change the z and y position here because they are just independent only on a single variable. But now let's skip this order. So x is now changing from 0 to 2, so it can be freely moving on here. So entire volume is lying in between the two sectional area when x equals to 0 and x equals to 2. Now y is only changing from 0 to x. So y equals to x is this line. This line, right? So this line. And y less than x means that y lies in here, right? But that's when only z is 0. So what really happens is when we have y less than x, we are looking at the entire one side of the volume cut by this y equals to x plane, right? So we are looking at the entire section here. But still, I don't want x to go exceed 2. So it's only bounded by x equals to 2. So once you have these two inequalities, you're kind of bounding your region up to here. So now that can be anything, so it can go forever to the top or bottom. But now we have a bound of z. So it says z is bigger than 0, so it cannot go beyond this xy plane. So none here, nothing here. And z is less than y. So you have to find where the z equals to y plane is. So z equals to y plane is right here, right? So can you imagine what it looks like? So here we have z, y equals to z plane, and this can be this way, right? So z equals to y plane is cutting through our prism, the infinite prism, but the prism is cut in the middle here because z is always bigger than 0. In the top, it's cut by y equals z plane. So it looks like this. So this one is one which looks like a very, very thin plane, but just because we are looking at the different angle here, so we have one plane of this, what is it, kind of a tetrahedron, but not exact tetrahedron, but tetrahedron-like shape here. So we have this one side here, and there's another edge behind this, hiding behind these two planes. So this is our volume V. So we want to find, let's see, I want to find the triple integral of V of 1 dx dy dz. So 1 means that the density is always constant 1. So let's try to use the Fubini theorem to find it. So basically it's going to be the same as the volume of this V, but we're going to check whether it's the case. So we have x from 0 to 2, y is from 0 to x, and z is from 0 to y, dz, dy, dx. Be careful about the order of this dx, dy, dz. You're taking the dz first, so dz comes first. So the next part is just simple integration. 1 dz is z from 0 to y. So this becomes 0 to 0x, y dy dx, and then what is it? Taking derivative of y, antiderivative of y, 1 over 2y squared, 0x dx, right? So we get 0 to x squared dx, and then taking derivative again, we get x cubed over 6, 0 2, you get 8 over 6, which is 4 over 3. Is it kind of right? So how do you get the volume of this kind of prism shape or tetrahedron shape? What is the formula of the volume of this shape? You first take the bottom, the area of the bottom, which is 1 over 2, right? What's the height? 1, right? So do you remember how to get the volume of the cone? What is it? 1 over 3 times? Yeah, area, pi r squared. The same thing here. I multiply 1 over 3. Yeah. So same here. So you have the bottom area, which is 1 over 2. Height, I sort of forgot the height here. Yeah, height here. Yeah. So height 1 times. No, is it right? So it's 4 over 3 or 1 over 3?
1 over 3, but we choose x, not 1, we choose 2. The x is,
Oh, axis is 2, sorry, yes, so that's right. So we have 2 times, oh, okay, yeah, so, sorry, so 2, and here the height of this triangle is also 2. So the area is 4, right? The area of 2 times 2 equals to 2 over 2, so it's 4 over 2 is 2, right? And the height, what is the height? Height is 2. Yeah. So height is 2, and then multiply 1 over 3, so you get 4 over 3. The same as our integration. So now I want to do something different. So I want to change the order of dx, dy, dz. So I'm emphasizing this because this is a common mistake the student makes. And what they do is the following. So I want to rewrite my triple integration, dx, dy, dz, in the following way. So first dx, dy, or dz. Okay? So I want to integrate x first. The integrand is the same one. The common mistake students make is, okay, I know that dx is about 0 to 2, dy is about 0 to x, dz is about 0 to y. What if I just took x is from 0 to 2, y is from 0 to x, and z is from 0 to y? Does it make sense? Can I do that? Is it okay to do that? No, why?
Then we ended up having our own variables.
Yeah.
And we were able to find the
Yeah, the final result is about y, right?
yeah.
Well, we want to get a number, so it doesn't make sense. And what does this means is that when you have to go reading the meaning of our domain from the outermost. So we are saying that coordinate z inside of V is changing from y first, without knowing what y is, which doesn't make sense. And then the variable y is now changing. When the z is fixed, we say y is changing from 0 to x without knowing what x is. Also doesn't make sense. And x is changing from 0 to 2, no matter what your y and z is. So nothing makes sense in our settings here. So we have to choose differently about this range here. So look at this figure again. If I want to describe my x, y, z, bound of x, y, z from in the order of z, y, and x, now I go for z first. So look at all the points inside of V. Where is my minimum value and maximum value of z coordinate among all the points in V? 0 and 2. Yes, it's moving from 0 and 2. So now I fix z. So let's say z is here. So I fix z means that I'm looking at the section of this volume at the plane z equals to z here. So we have some section here. What does it look like? So first of all, let's see. If I look at the xy plane here at the height z, then so we have what is it? So we are looking at this part. So we have what does it look like? So it's confusing. So we have somewhere. Well, you just imagine with this picture. So I want to find the range of my y, this range. So what is the maximum range of my y? 2. Yes, y can always go up to 2 because that's right here. The y, maximum y is 2. What's the minimum? No. It doesn't look.
In the case of smaller triangle, yes.
Yes, the smaller triangle. So, let's see. So this plane is y equals to z plane, right? That's the minimum y you can get, right? Has to be bigger than, y is bigger than z from here, right? So z is the minimum value of y. Cannot go beyond, below z here. So now let's assume that z and y are fixed. What's the range of x? What's the maximum of z? What's the range of x? What's the maximum value of x first? So here, this is maximum. Here is the maximum. X can be up to 2. What's the minimum? So minimum is right here. Minimum is right here. And this line is coming from where? It's coming from x equals to, y equals to z line. So this one, so this one is it's coming from y equals to z. And we know that x is bigger than y, right? So x is bigger than y, so y here, right? So x must be bigger than y. So you have to go for this line. So this line is the minimum value. Okay. So this is the correct range of x, y, and z. So how do we know it's correct? Let's compute. If you get the 4/3, then it's probably correct. So let me see here. But first, let's take derivative of 1 with respect to x to get 2 minus y, right? dy dz, and then derivative of this, we get 2y minus 1/2y squared, z2 dz here, and 4 minus 2z minus 1/2, 4, yes, it's 4 minus z squared dz, right? And then, let's see, 4 minus 2 becomes 2, so we have 2z minus z squared plus 1/6 z cubed, 0, 2, right? So we have 4 minus 4 plus 8/6, so it's 4/3. So, well, rigorously, it's not a proof that our limit is correct, but this is correct. So whenever, what I'm emphasizing is that whenever you use Fubini theorem, and mostly you need to use the Fubini theorem to compute or define or give a meaning to your triple integral or double integral. But when you need to change the order of the iterated integral in your Fubini theorem, you have to be careful about the limits of x, y, and z. So whenever you try to think about the proper range of each coordinate, try to make a geographic picture of your region and then make the change. All right, so any questions about this? So far we just just talked about the Fubini theorem and its examples. So if you want anything, any other examples, I can give you more, or any questions about the concept, we can talk about it again. Any questions? No? So the next thing I want to talk about is integration by parts. So we talked about integration. I gave you the formula of integration by parts for the single variable case. So there is an integration by parts in double and triple integration. So the meanings are the same, but it's a bit complicated. So let me fix this part and give a description of what it means. So I'm gonna write down the theorem and then give a meaning, explain the meaning. So let's say we have a map from D to U. So D and U, let's say these are two-dimensional region in two-dimensional space. And let me say D is inside of XY plane and U is inside of UV plane. So U and V are functions of X and Y. And let's say this is 1-to-1. And let's say we have a double integration of a function in terms of U and V over U, domain U. Okay. So integration by substitution says we can compute the same double integration by the following way. So instead of taking the integration in terms of UV, you can take integration by dx dy. But you have to change your integrand in terms of x and y. I mean, it's easy because you just simply plug in or substitute u and v by the formula of u and v in your one-to-one function t. But you also have to multiply something, which is uv over x, y. So this is just notation called Jacobian. This is defined to be there uv, there x. Y is the determinant of ux, uy, vx, vy. So sometimes people exchange the off-diagonal parts here. Instead of ux, uy, they put ux, vx, and uy, vy. But I like this way because you can see that this is basically the same as the derivative of your function t. Right? The same thing. The t is a 2-to-2 function, and you take the derivative, it's 2-by-2 matrix. And Jacobian, this inside thing is just the determinant of this 2-by-2 matrix. And the important thing is you have to have an absolute value sign here. So the bar here is not the symbol, it's the symbol of the Jacobian. It's the symbol of absolute value. So this is called the Jacobian. This is called the Jacobian. Okay. So what does that mean? Okay, so suppose that you have D as a shape of a rectangle, and let's say our T is just T here. So let's not give a concrete formula here. So let's say you have a T, and somehow this D is changed into some weird shape over like this one. Okay. So originally what I want is integrating a function defined over U. So function f is a real valued function defined on U, and I want to find out the double integral over U. But it's really hard to make, sometimes. I mean, you can define it by putting U into bigger rectangle, and just as we did in the beginning of our class, you can define the double integral, but to use the Fubini theorem is getting sometimes harder when the shape is irregular. So if you can find a one-to-one map from well-shaped region like D1, like this rectangular region D, which maps one-to-one fashion to this irregular shape U, and then if you take this composite here, you're not changing the value of function. You're just looking at the same value of function. It's just a matter of perspective. Either you take a point here, or you take a point here to find out the value of function. So it doesn't really change the function, but now you change the domain here, right? So you're basically you want to find area under the function of this function over u, but when you take the integration over d of this function, you're changing your domain of your function. So you need to make up the difference between the area of d and u. So here I just put the horizontal line and vertical line, and let's say these vertical lines right here is corresponding to these vertical lines here, right? And also horizontal lines on the other side here. So then when let's say I take dx dy right away. What I'm saying here is that I take a value at some point which corresponds to point in here, and value are the same. Value is the same, so it doesn't matter whether I put x and y here and then or here to find the value. That's okay, but the problem is dx dy is the area of this small region, and this small region corresponds to this small region here, but they're no different, and they have different area. So this area is dx dy, but what we really want in the beginning is du dv. So the area is dx dy, and this is not the same as area of here, du dv. So here again, I want to multiply the area of u, which is du dv. I cannot just simply multiply the area inside of its y plane, dx dy. So I need to modify my area of dx dy into du dv by multiplying this Jacobian here. So why do we need to multiply Jacobian? So that's the key part. So du dv dx dy, multiplying dx dy, this whole thing is now becoming du dv here. So let me explain a little bit. So at point, let's say we have a point x comma y. So this is dx, so let's say del x, this is del x, and this is del y. So remember that we denote our vector moving from point x comma y as del x and del y, the partial operator symbols here. And when I change it to change my perspective into the UV plane, so xy point is now mapped into u comma v. And then if I move xy horizontally in the straight line, the point uv is not moving horizontally in the straight line. It's moving in some kind of curve. It's a kind of curve. And also when I move straight up, it's not going to move straight up in the UV plane. It's going to move in some weird direction in a certain curve. But when I just started to move in this velocity, then I can assume that this UV is following some kind of tangential direction to this curve. So it's going to move in this direction and that direction. And that is del u and del v. Okay? So when I take the small area inside of v and u, what I'm taking is the area bounded by these small tangent vectors. So these small tangent vectors. Okay? So this is dx dy, and this is du dv. The ratio between these two areas, dx dy and du dv, is the Jacobian, dx dy. So in some sense, so this is just a symbolic notation that dx dy du dv means the small area surrounded by these vectors. But if you count this as same as the Jacobian, then you can see that du dv over dx dy cancels with dx dy to get your du dv on the left hand side here, du dv over u here of the function. Okay? So you can look at my book to think about why this is the case, why this Jacobian gives the ratio between the small area. It has to do with this vector cross product of two vectors here. And I I think it's easier, it's important to know how to apply this integral by substitution. So let me give an example before I move on. So let's see. So here is an example. Here. So we have D given by two sets of inequality, one here and one plus y over 2 here. So D consists of all the points x, y satisfying these two sets of inequalities. So what does that mean? So look at this 2x minus y. Let's draw the picture of this. When 2x minus y equals to 0, that means just y is 2x, right? Like this is the y equals to 2x. So that's when this is. And when 2x minus y equals to 1, then it's y equals to 2x minus 1. So it has a y-intercept minus 1, so it's around here, right? So this inequality means that our domain lies in between these two strips. And how about this one? So we have x plus y equals to 1 means that you have line here, and x plus y equals to 2 means you have a line about here. So your domain D is in between these four lines, right? So I want to find the integral of xy over this domain, dx dy, d. So you can do it by using definition, but I want to use the Fubini theorem. But in order to use the Fubini theorem, you need to have somehow nice formula to bound the maximum value of y or minimum value of y, or vice versa for the minimum value of x and maximum value of x. But it isn't, because you have a sharp corner, so you have to split into some at some point, and it's getting complicated. You have to split your domain D into several regions in order to use the Fubini theorem. Once you get the once we see the application of this integrated by substitution, I'm going to show you how to do this by Fubini theorem. But let's use the integration by substitution for now. So here I have the D here. Can you see this writing here? Anyone in the back side? Is it okay? Okay. So when you want to see the D, xy, dx, dy here, what do you want? So so originally this D, so you have to be careful about this notation here. So what we want is the integration over the codomain of this one-to-one map. So our codomain is D. Okay, it's kind of opposite situation. So let me change it to U and xy to U and V here. U and V, and x and y to be U and V. But everything is the same except that I just changed the symbol here. U V U V. So I want this. Okay, but I want to change it to different domain, different double integral. So I want to find the t that sends any point D, which is inside of xy plane, to U in one-to-one fashion. And I also want this to be nice domain, nice shape domain. The rectangular shape is the best. So what can be my candidate? So if I just say this entire thing is x, and this entire thing is y, then x is from 0 to 1, and y is from 1 to 2, right? It's 2, right? Very nice domain, D, just rectangular domain, right? So how about t? What is the formula of t? So xy is mapping into u and v, but what we know is x equals to 2u minus v, y equals to u plus v. Not u equals to some formula of x and y. So I need to change this to, in terms of u, explicit for u. So let's add this together to get 3u on the right, and you get x plus y. So u is 1 over 3 x plus y. And v, what is v? V is y minus u, so it's going to be y minus u, so it's 2 over 3y minus 1 over 3x. Okay? So that's u and v in terms of x and y. So that's my t. That's my t sending b to u. Is it 1 to 1? It has to be 1 to 1 in order to use the this integration by substitution. So it is 1 to 1 because it's a linear map. So whenever you have a point u comma v, whatever the value is, you can find unique x and y by solving the system of equations. So you have a one-to-one map here. So what does the substitution work? Substitution says, so you can change your integration of, so originally this integration in terms of uv over u into the integration over d, right? And u and v is just written as the integration, the substitution here. So we have u as 1 over 3 x plus y, and v as 2 over 3 y minus 1 over 3 x dx dy, right? And then, so before dx dy, what do we need? We need Jacobian. There u, v, there x, y, dx, dy, right? So what is del u, v over del x, y? You have a 2 by 2 functions. It's just the determinant of your derivative. What is the derivative? What's the first coordinate of your derivative? You take the derivative of u in terms of x, which is 1 over 3, and then you take the derivative of u in terms of y, 1 over 3, and then you get 2 over 3 minus 1 over 3. So this is minus 1 over 2 minus 2 over 9 minus 1 over 3. So you don't multiply minus 1 over 3. You want to multiply the absolute value of minus 1 over 3, which is 1 over 3. So this integration becomes integration over d. Now you can use Fubini theorem, right? It's a rectangular shape. 0, 1, 1, 2 of 1 over 3 times, the 1 over 3 comes from the Jacobian, 1 over 3 x plus y, 2 over 3 y minus 1 over 3 x, and this 1, 2 is about y, dy and dx. Okay, let's compare this formula. So this is doable. I mean, it's not too complicated. Let's compare this formula with our original another approach. So let's try to think about the exact shape of u. What does u look like? So here, this one, okay, so this is better. So this is u and this is v. So here is our v equals to 2u line, and this is v equals 2u minus 1 line, and this is u plus v equals to 1, and this is u plus v equals to 2. So let's find out the coordinate of all intersection here. So, okay, the first one, what is it? So u plus v equals to 2, v equals to 2u means u is 2 over 3 and v is 4 over 3. And how about the intersection here? So intersection between these two, 2u minus 1 equals to 2 minus u. So u is 1 and v is 1. Okay. So how about this one? So this intersection with this, you get 1 over 3 and v is 2 over 3. Okay. So how about this one? So intersecting these two, so this one equals to 1 minus u. So we have u equals to 2 over 3. Oh, so it's actually nicer than I thought. Okay, so we have v equals to 1 over 3. So they are on the same vertical line. So you can kind of split your domain u into two parts, which is u1 part and u2 part. So you can, if you want to use the Fubini theorem without using integration by substitution, you have to split your domain d, domain u, into two parts. First for u1 and second for u2. And the u1 now you have for x from what? 1 over 3 to 2 over 3. you have range of y depending on these two lines, right? So for u1, you have u range from 1/3 to 2/3, and then v is ranging from, the minimum is this line, which is 1 minus u, and the maximum is this line, which is 2u, right? That's the u1 integration. Let's omit this part. The integrand is the same, so uv here. And then, what is the integration for u2 part? So the u2 part on the right is, u is ranging from 2/3 to 1, 2/3 to 1, and then v is ranging from this line, which is 2u minus 1, to here, upper part, which is this one, right? So v equals to 2 minus u, so uv. So you have to take the integration twice and then add them together to get the entire integration. Well, it depends on you. It depends which one you think it's easier, but you can do it either way of solving this. This is kind of a nice example, so I might think of this as some midterm final exam maybe. So you understand this, that we have what we are going to compute is the same thing. So you want to compute this, you can go for the Fubini theorem directly, or you try to make your integration a bit simpler by changing your domain of your integration into a simpler shape. And then once you get there, you can still try to use the Fubini theorem there.